Hi, and welcome to Dr. V's AP Chemistry webcast. Today we're talking about electrolysis, electrolytic cells, and quantitative applications of electrolysis. I want to give a shout out to Maddie and Julia, who really did the bulk of the work putting this presentation together. They're here to help me get this recording out to everyone. Now, electrolysis is actually a fairly important topic in AP Chem. It's something that shows up on a regular basis on the AP exams. And so let's talk about our objectives for this so that students know exactly what they need to be able to do. We want to differentiate between voltaic cells and electrolytic cells. We need to define what's going on in electrolysis and really talk about what this means, and electroplating and how it works. And finally, we'll do a quantitative electrolysis problem. We're going to master this skill. All right, so in general, I find that students come into AP Chem much more familiar with voltaic cells than electrolytic cells. So let's do a little compare and contrast so we know what's going on here. All right, we'll start with a visual comparison. So for both of them, we have an anode and a cathode, right? We have electrons traveling.
Do electrons flow from anode to cathode in both voltaic cells and electrolytic cells?
Yes, that's actually very much the case. But in voltaic cells, it's happening spontaneously. And in electrolytic cells, we actually have to drive the reaction with an outside power supply. All right, we have oxidation occurring at the anode. We have reduction occurring at the cathode. This is true in both kinds of cells, but they're fundamentally different. And this is what Julia was asking about. In the voltaic cells, it happens spontaneously. You set it up, the reaction just occurs. And in an electrolytic cell, we need to drive that reaction. It doesn't happen on its own. All right, so let's do a little deeper comparison of these. All right, in a voltaic cell, we're taking our chemical energy and we're having a redox reaction occur, and it's producing electrical energy in a useful form, right? A battery, basically. All right, whereas in an electrolytic cell, we're using the electrical energy to drive the reaction because that reaction doesn't occur spontaneously. Right, and so that's actually kind of an important point. So in a voltaic cell, the redox reaction is spontaneous, and Ecell will be a positive number. Whereas in an electrolytic cell, the reactions are not spontaneous. We have to drive them, and Ecell is negative. Right, and that's an important thing when we're going through them. In a voltaic cell, the half cells are separated by a salt bridge so the ions can move from one compartment to the next. Right. In an electrolytic cell, typically we've got the two electrodes placed in the same sample, and it might be a molten electrolyte, or it might be ions in solution. All right, so there's a couple of different ways to do electrolytic cells. All right, so in voltaic cells, the anode is considered to be the negative electrode, that's like the negative terminal on your battery, and the cathode is the positive cell, or the positive electrode. It's flipped in an electrolytic cell. Now, the College Board is no longer testing you on this explicitly, but if you're in a college level class, or you've got me, I'm going to expect you to know this anyway. So in an electrolytic cell, the anode is considered to be the positive electrode. All right, again, in voltaic cells, we're releasing electrical energy in a useful form as opposed to a sustained energy input in our electrolytic cells from our battery or our power supply. Gibbs free energy is negative in a voltaic cell because these are spontaneous reactions, whereas Gibbs free energy works out to be a positive value for our electrolytic cells because it's not a spontaneous process. All right, so understanding these differences is something that you really need to be able to do. All right, let's go on and talk about electrolysis a little bit more. Essentially what we're doing is driving a decomposition reaction. All right, so in this image, we've got sodium chloride ions, sodium ions and chloride ions in solution, and we are passing an electrical current through, and the chemical reaction that occurs is the electrolysis reaction. So in this case, we're taking chloride ions and making chlorine gas. And in principle, we'd have sodium ions making sodium, but the truth is, actually, in water, we'd actually have that water doing that reaction. It's very hard. If this is a molten salt, we can get it to happen, but if it's in water, we'd actually have a different reaction. So it gets much more complicated with aqueous solutions. But if it's a molten salt, we'll actually just do a decomposition reaction. Right? Molten salts need very high temperatures in order to do the electrolysis reaction. So this is not something that you would typically do in an AP class or a freshman college class. Aqueous solutions are much more complicated to predict, and that's going to be a whole separate webcast that we haven't even created yet to talk about prediction of electrolysis for aqueous solutions.
Is there a salt bridge in an electrolytic cell?
There's really not a salt bridge. Everything's all in the same container, so the ions can just move it. That's why we need the molten salts or in solution so that the ions can move. A lot of times when we're doing this, the electrolytic cells, we're doing it with inert electrodes, right? So we did an electrolysis lab in class and we used graphite rods. They didn't get involved in the reaction themselves. Really what they were doing is just providing a surface for the electron transfer. Platinum wire can also be used as an inert electrode. And in AP Chem, that's really the emphasis that we have. You can have active electrodes that actively get involved in doing the reaction, but and they participate, and they are part of electroplating. But in terms of writing out the cells or describing them, the College Board hasn't put this on the AP exams. All right, and writing reactions with active electrodes is not really something we have to worry about specifically. But you do have to have an electrode so that the electrons have a place to do their transfer. All right, so our main emphasis really is the quantitative aspects of electroplating. So we've got an image here. All right, we have an aqueous solution of nickel 2 sulfate. So we have nickel ions and sulfate ions, but we don't really care about the sulfate ions. They're not getting involved in this reaction. And we have a nickel anode. And what we're going to do is take the nickel ions and basically reduce them at the cathode, all right, because reduction occurs at the cathode, all right, and that's really what's going on here. So we're going to, that nickel anode is actually going to get less massive as we oxidize it, and we're going to end up making nickel metal depositing on the steel cathode. So let's look at our practice problems and go through the math of this, which is something that we really need to be able to do. Right. Let's talk about our general strategy. There's actually two types of electroplating problems you can do. In the first type, right, we're given a current, usually in amperes, and time in seconds. If your time's not given to you in seconds, what should you do?
Use factor label.
Use factor label, and we'll convert that. All right, and so you might ask for the mass of whatever metal you're depositing. All right, so you can find coulombs by multiplying your amps times your second. All right, so current times time would give you coulombs, and then you can use the Faraday to find moles of electrons. And from there on, you need to look at the half reaction. What metal cation is depositing to the metal, and how many electrons does that involve? And so you can find the moles of the metal, and then you just multiply that by your molar mass. That's easy. That's the easy step. So actually, these problems, the way we approach them in class, is really just a giant factor label problem. Right. The other kind of problem that you sometimes will encounter is where you're given the mass of how much stuff plated and the current in amperes, and you want to know how much time did that have to run. You could also, another twist on this might be, you know, the grams and the time, and you want to know what current you needed. All right. But the strategy really would be quite similar. So we have to take our grams of metal deposited and to convert that into moles, and then from the half reaction and the number of electrons involved in that reduction step, how many moles of electrons were involved. And then from the Faraday, you can find coulombs, and then we can use amps times seconds to find the missing piece. So that's really the strategy that we're going to go through. Are you guys ready to do a problem?
Yeah.
All right, you guys mapped it all out, so we should be in really good shape. Let's do a practice problem. All right, so how many grams of copper will plate out if 3.70 amps of current flows for 2.5 minutes in molten copper 2 chloride? So we have this really hot sample of copper 2 chloride. Woo-hoo. All right, so we do have a lot of equations. We know that the amps times the seconds will give us coulombs. And we know the Faraday, that's on your formula sheet. It's not like you have to memorize it, although students often find they use it so often that they end up remembering it anyway. The molar mass of copper is 63.55 grams per mole. And what else do we need to make sure we keep track of, folks?
Units.
The units, all right? You want to make sure your time is in seconds, okay? Because that will make things much easier. So you have to do a bit of conversion there. Otherwise, you're going to run into a bit of a pickle. All right, so factor label is our best friend. All right, we had a time in minutes. We're going to convert that to seconds, all right? And once we know our seconds, we can find coulombs, all right? Now, you might want to consider before you go any farther in the problem, maybe pausing the webcast, try to do the problem on your own, and then compare your work to what we're doing here. It's always a good strategy. So we know amps times seconds will give us coulombs, all right? And once we've got the coulombs, we can use the Faraday. And what do we have to do with the Faraday here? We're actually dividing it, right? Because that will give us moles of electrons.
We have to make sure we have 2 electrons.
Right, because we're taking copper-2 ions and reducing them to copper metal. That's a 2-electron process. So we really only care for the half reaction. What's the cation? What's the metal? How many electrons did that take? All right, so there's 2 moles of electrons for each mole of copper. All right, and 1 mole of copper has a mass of 63.55 grams. And then we get an answer. Now, what's the other thing we have to pay attention to?
Sig figs.
Sig figs. We want to make sure that we report our answer with, we don't want to add precision. So we're really only allowed 3 sig figs because I had 3 sig figs in my amps and 3 sig figs in my time. So I'll report my answer with 3 sig figs. And we know the Coulomb, the Faraday, lots of precision, and everything else we know to lots of precision. So that's what determines our answer. Sound good? All right. Let's go on and do the problem where we're going in the other direction. All right. Because it's good practice. All right, so here's the problem. All right, the half reaction to deposit magnesium metal when molten magnesium chloride is electrolyzed is magnesium ions plus 2 electrons makes magnesium metal. How long in seconds would it take to produce 20 grams of magnesium at a current of 75.0 amps? Sounds good? All right, so again, pause the problem, try to do it on your own, and then we'll come back and compare our work. That's really the best strategy. Just watching me do the problem doesn't help you learn how to do it on your own. So again, we know amps times seconds gives coulombs. We've got the Faraday, the molar mass of magnesium. We can just look at our periodic table, which of course you always have handy. We know that it's a 2-electron process to go from magnesium ions to the magnesium metal, and then we're ready to go. So in this case, we're starting in the other direction. We'll start with the factor label to get to coulombs. Right, is our strategy. All right, so how are we going to set that up? Well, we know that there's 24.3 grams in 1 mole of magnesium, so that's an easy conversion to moles. 1 mole of magnesium, we needed 2 moles of electrons for that reduction half reaction. All right, multiplied by the Faraday, that gives us coulombs. Now look at all that precision. Obviously we don't know it to that degree, but we don't want to round until the end. We don't want to go too soon. So we have this coulombs, lots and lots of coulombs, and then we'll go back to our amps times seconds gives coulombs. We can rearrange that, right, fairly easily, right, and then we get a unit, we get time, all right. But again, what do we have to remember?
Sig figs.
Sig figs, all right. We really only know this to 3 sig figs, and so we'll report our answer as 2,110 seconds. Sounds good? I think we accomplished quite a bit in this webcast. We're in very, very good shape. Now, if you're feeling like you need a little more practice with these problems, they're not particularly difficult, but you do want to practice them so that you feel very comfortable with them. I recommend the online homework site. If you haven't used it, it's a really helpful site with lots of practice problems, but problem number 40 is all about electroplating. So you could go there. Here's the link. This is from Cal State University at Domingo Hills, and they've had this website there for a long time. And if you want to do some extra practice problems, I recommend going there and just doing a few until you feel really comfortable. All right, we'll stop here.